my first question to the panelists was just to have them introduce themselves and to just say, like, who you work for and what you do that's related to chemistry applications. So I'll just.
Okay, hi, my name is Michal Krompiec. I'm the scientific project manager in the quantum chemistry group at Quantinuum. I work with customers and our internal technical team to build proof of concept solutions and develop roadmaps to quantum advantage for specific customer use cases. My background is in materials chemistry. I used to be a bench chemist back in the day, but yeah, these times are long gone. Over to you.
Sure. Hi, everyone. I'm Sonika, Johri. I lead the quantum applications team at IonQ, which is a team at IonQ that designs applications and algorithms for near-term quantum computers. We work on, our focus in this year has been mostly on machine learning, chemistry, and optimization applications. And in chemistry, a couple of examples of our projects is the one that you just heard Luning and Carl talk about. It's a collaboration with Accenture. And tomorrow we'll also be presenting results from our collaboration on quantum chemistry with Hyundai.
Okay. Yeah, my name is Scott Chen. I'm the head of materials discovery at OTI Lumionics, and I oversee the materials discovery division from, basically concept to preliminary synthesis. So I lead teams which develop quantum chemistry simulations, whether they're on quantum computers or whether they're on classical computers, thermodynamic simulations, all for basically trying to simulate materials as accurately as possible. OTI predominantly focuses on the OLED industry. It's where we have a lot of knowledge and a lot of application engineering. So basically, I collaborate with a lot of my coworkers also on kind of the application engineering and the preliminary synthesis as well.
Hi, so is this working? Hi, so my name is Chandan. Yeah, hi. So my name is Chandra Kumar, and I'm working at BMW Group. So I focus on material science discovery and quantum computing within BMW as lead, quantum computational chemistry lead. Our interest is to look into battery research, fuel cells, applications, and how we can benefit from quantum computing and quantum chemistry research. We also collaborate within our business unit. We also, together with other quantum solution providers, closely work with them on some of the problems. And I also collaborate with our consortia partner for certain research topic. Yeah, that's all.
All right, so I thought we would first start with some rampant speculation. So I'm going to pass out these little slips of paper to each of you. If you could just pass them down, pass these pens down. And so, this conference is called Q2B, Quantum to the Bank. So I want to know from these lovely scientists, I want them to speculate what they think is going to be the first profitable application within this chemistry space and when. And there are no wrong answers except when the future happens and the answer will probably be wrong. But anyway, I just want to know so we can kick off this, discussion. And then if you guys can also, speculate, maybe if you disagree, I will solicit your opinions as well. All right. Okay. All right. So I guess let's just go down the line. So, yeah, what's going to be profitable and when?
Catalysis in about 5 years' time.
So I think it would be one of the applications that we're working on. For instance, with Hyundai, we're working on battery chemistry and also metal organic catalyst for hydrogen fuel cells. So likely one of those. And I think it would be around the time we have between 40 to 60 very high quality qubits. Let's say, IonQ has a benchmark that we call algorithmic qubits, AQ. And when we are around between 40 to 60 AQ, we should be beyond the simulation capability, well beyond the simulation capabilities of classical computers. And at that time, I expect we'll be able to find some system that has enough correlations that cannot be captured anymore by classical computers, but can be captured to more precision within a shorter amount of time by quantum computers.
On a noisy computer?
High quality. But
Okay.
there's no such thing as a noiseless quantum computer, and never will be, right? There's always going to be some amount of noise. And we just always have to get to as high precision as we can within that boundary.
And you?
Yeah, I'll just say it. Organic semiconductors, which is the field I work in, I'm just going to say it as blatantly today because we did at OTI. But we also use an emulator, so I don't know if that's necessarily considering as cheating or not at this point.
Wait, can you explain? What
Yeah,
you
so
mean, like the
basically,
simulator rather than
yeah, we have an emulator which basically replicates that variational quantum Eigen solver simulation perfectly, and so we can do it at mass scale. So we can already design chemicals that can easily be profitable. But I would say, like, if you're a chemical company looking at that, you have to first get your value chain of being able to take a simulation result and carry it all the way to synthesis first, and then carry it into actual product form. You have to be really good at that side first before you can actually really start saying that a quantum computer is going to, develop. Now, so, I think 5-year time frame is actually pretty correct because it's going to take a lot of other companies 5 years just to build up that infrastructure to take a simulation result to market.
Yeah, so I would say thermodynamics of chemical reactions. So it's less complicated than many of other processes, so it might benefit in earlier stage. And in terms of timeline, I would say that, same 4 to 5 years. But then it all depends how much development goes into the hardware and the quantum algorithms. I mean, lots of if, but I would say thermodynamics.
Okay, can you give an example in what
so
context?
like if you want to see how chemical reactions are happening, one of the easiest thing to look into the energy. So it's a single point energy calculation, very simple. And then what you would like to do, I mean, even for like organic molecules, even for correlated systems, exactly know the energy of every single species in the reaction. And then if you know that, I mean, then you can use those numbers to do some sort of microkinetics and benefit in the chemical reaction process. Like if you want to optimize certain process within chemical industry, that you might be able to do it. It's very simple in a way from the chemistry point of view, but I would say that it might benefit first compared to same as others.
Okay, and since you went first, you want to elaborate a little bit more on catalysis?
Well, it's also about microkinetics, as Chandan said. So once you can compute the energies or free energies of all the species in the catalytic cycle, especially in the rate determining step, you can compute the reaction rates precisely. And it's extremely important to have a sufficiently accurate method to do it, because even small errors in the rate constant translate to huge errors in the prediction, because the rate constant goes into an exponent in the equation. That's why we need really, really precise methods, and that's why DFT or other classical methods are often not good enough.
Okay. And then Scott, actually, you mentioned infrastructure taking simulations to the market.
Mm-hmm.
Can you give some examples of what do you mean by infrastructure?
So infrastructure is like, how do you actually convey a simulation to a chemist, right? Because otherwise you're kind of doing the reverse process where your chemists are just synthesizing materials, however they feel. And sometimes they have really good intuition, so they do make good choices, but they're not being really led by the simulation. So how do you actually transfer that information to them? How are they going to actually utilize that to make appropriate decisions? And how are you going to actually make sure that your material can end up being validated, like, to the point of catalysis? in chemical engineering parlance, we always had a joke where basically people would simulate a catalyst, and then they would be like, well, I think based on this simulation, the reactor should be 50 liters. And we would say, oh, well, if they simulated it, quadruple the size, at least, of the reactor, just to make sure that nothing bad happens. Whereas if a chemist synthesized it and measured it, we'd only double it.
Okay. Okay, so now I'm going to ask some questions about the state of the field, and so I'm just going to call on one of you sort of randomly, and then after that, like the rest of you can chime in if you have things to say. So I guess first. So in the field, people have been using this concept of quantum advantage to describe a state of like basically a milestone for hardware, and I was wondering in this space in chemistry applications, what would quantum advantage mean, and like is it even a relevant metric? So I guess let's start from the opposite end, Chandan.
Yes, so as I understood, this quantum advantage, one would like to see that whatever classical methods we have, like accurate, that's available in the code. You can put it on SPC and do some simulations. But then the system size grows and you cannot really do it. So Michael has this slide where he would like to have that one of the, let's say, workhorse DFT, that cost is somewhat we can afford to do it for even for bigger systems, but as accurate as that we do it with very high accurate methods. So this is something, a sweet spot that we would like to achieve, and then we benefit from we do quantum computing or quantum emulation for the large systems, use those numbers to further drive the material designs, chemical synthesis optimizations, this sort of process.
I think in a very short summary, it's, quantum advantage comes when you can basically do anything, you can do any sort of quantum simulation that outperforms CCSD. That's where you have quantum advantage, and quantum supremacy in quantum chemistry is when you can match the full CI solution without exponential scaling.
I would like to disagree with this because it doesn't take much to beat CCSD, and reaching full CI for most systems is pointless. It all depends on the use case and what kind of accuracy you want for your system, and it depends also on the degree of electronic correlation in your systems. It's strongly correlated or weakly correlated. To me, quantum advantage in a practical sense means beating the benchmark workhorse methods like DFT, and beating the benchmark multi-reference methods like CASPT2 or related. Beating means being able to tackle larger systems and having systematically improvable accuracy, which is not possible with methods like DFT right now.
I think I would agree with this perspective more, because basically quantum advantage in this area means that you can improve upon the best classically possible result for up to some precision for some systems, right? It doesn't mean that you have to solve the problem exactly for all possible molecules, let's say, right? Even if you can identify a handful of molecules for which you can do better than what classical computers can, right? By some percentage, that's quantum advantage, right? Then of course, if you can translate that into if those molecules have some real world relevance, that's even better, right? And I think, I'm not from the chemistry community, I'm from, condensed matter community, but often how we solve problems is that, you take, if you have a Hamiltonian that has strong correlations, you can treat, you do methods where you treat most of the system approximately, and then you isolate part of the system that has strong correlations, right? And you treat those exactly. And I foresee some methods like that having great success, where you solve a large part of the problem on the classical computer approximately, and then some part of the problem that's really tough has exponential scaling in order to solve it accurately. You farm that out to a quantum coprocessor, and in this way you gain quantum advantage over the best possible purely classical methods. And so you have this incremental approach to fully solving a problem, or solving it up to the point where you have commercial relevance.
I totally agree, and this is very similar to what we're trying to do. And I would like to pick on what you said, that it's not about exactly solving a problem. And as you said, in chemistry, the strong correlation, if it appears, it is almost always localized in terms of space or energy scale. So it really, there is no point in trying to solve the full system with full configuration interaction or exact diagonalization, as you would call it in physics. If you had to do it, then indeed a quantum method would have always an exponential advantage to the naive classical method, but that's not the point. It's really system specific.
Okay, I just want to clarify the two sort of viewpoints. So you two were saying that quantum advantage would be this sort of hybrid method where you put part of it on a classical computer and part of it on a quantum computer, and then whenever it's sort of this heuristic way where, like, once you get value out of it, where it does better than just the classical algorithm by itself, that would be quantum advantage. And then Scott, you were saying that you were not including sort of this hybrid approach. Well, I guess, like, do you want to clarify?
So in order to execute the hybrid approach, so I always look at things from a materials discovery standpoint, not from like a scientific academic paper publication route. If you have to do something where you're basically constraining your strongly correlated system, you have to know that a priori. But the problem is that your molecule generator is spitting out hundreds of thousands of molecules basically per day, and they have to be simulated and funneled in. So oftentimes you can't have someone with a PhD sit there and screen every single molecule and look and say, yes, this one has strongly correlated system in this work, because this is what we deal with OLEDs. You can basically change the metal center and change out the strong, or you can basically take strongly correlated systems and flip them into weakly correlated systems, or flip them into mediumly correlated systems, which are not really well defined. But if you are trying to do this in an automated, rapid fashion, you can't have someone sit there and comb through every single one, because now they become the rate limiting step. So you're no better than the chemist who just goes out there and synthesizes it.
I
so that's
strongly disagree with this viewpoint on several levels. First of all, it's not necessary to have a human to do it. There's plenty of algorithms to do it. And secondly, your systems will almost always be too large for a direct solution of the whole electronic structure once you use a sufficiently large basis set. And finding a strongly correlated subsystem in chemical matter is usually quite simple. So I don't see the point. Why would it be a problem? But maybe let's move this part of the discussion to the party afterwards.
Well, I guess this is the difference between someone who has to discover materials every day.
Ooh.
Maybe not. Because I have not found a system that actually works, and I can show evidence where it does not work.
Fair enough. And go and publish it.
All right. When I was preparing for this, somebody told me about a recent provocative paper which said that, so it was, the last author was Garnet, Chen, which said that one cannot assume exponential speed up for chemistry problems generically. So I was wondering, what does that, the fact that, would you agree with that? And also, like, what is the implication that you can't assume exponential speed up?
To some extent, yes. So Garnet, Chan, and collaborators make two arguments. One is that to execute a quantum phase estimation, you need to prepare a trial state which has non-zero overlap with the state you're seeking. And this state preparation is already quite expensive, potentially even exponentially expensive, which would kill your quantum advantage in the end. And this is a very strong argument, especially if you apply it to large systems where you cannot test it. So this initial state preparation would probably need some heuristic. And it's hard to talk about the complexity of heuristics before you try them. So I think this is a potential threat, that the actual advantage will not be exponential. But it's not really a problem. The advantage of DFT over coupled cluster is maybe 3 orders, so cubic versus 7th power. But this is absolutely phenomenal. So we don't need exponential advantage to have a business. The other argument they are making is that classical heuristics for solving strongly correlated problems, such as DMRG, have polynomial cost, in contrast to naive solutions which are exponential. Some experts in DMRG disagree with this strongly, pointing out that DMRG in a three-dimensional case actually does scale exponentially, which invalidates Garnet-Chan's argument. But the first one still stands.
Yeah, so, okay, so I would like to generalize, look at this from a bit higher level. And that is that for almost every technique, especially if it's heuristic, you can always find some adversarial example and say it doesn't work for that example. But that's kind of a useless statement, right? Like, if it works for 90% of the examples and it doesn't work for 10%, but you can still make the statement there, it is not guaranteed. But what economic or real life relevance does that have, right? Like, for instance, let's take the example of classical machine learning, right? There are theorems that say that training like a deep neural network is an NP-hard problem. But does that mean we get scared, like we don't use classical machine learning? Yes, it works for many problems. I'm sure you can construct some, contrived example for which it wouldn't work. But that's kind of a hollow statement for me. Right.
That's a very good argument. I mean, in computational chemistry, Hartree-Fock method is it's proved to be NP-hard, but in practice it's trivial.
Do you have anything to add?
No, Michael actually summarized it incredibly well. The paper, including the caveat associated with DMRG, which is that, the famous question is, they always say like, chromium dimer is actually one of those problems which DMRG is routinely benchmarked upon. And it actually does a fairly good job comparatively to a lot of other classical methods. And as you very succinctly pointed out very well, one of the favorite comments that some condensed matter people will mention is that they'll say, well, what about chromium trimer? And then the scaling just falls right off a cliff. I'd also point out one kind of interesting caveat about the paper that I think they kind of, very high level did is they only really mentioned that it only really works for like very sparse, sparse matrices. And in that context, there's a lot of kind of tensor tricks which you can use to kind of address sparse matrices that work really rapidly. GPUs do this all the time from a computational standpoint. So there are a lot of like computational tricks on the back end that you can use to kind of be like, well, there's no quantum advantage in this, there's no quantum, there's no reason to use a quantum computer in it. But I would then challenge, well, what happens when the matrix is no longer sparse? What happens as it gets more and more complicated as you go to a higher level basis set? I think that until you can actually really prove and make a case that's, they didn't make a case that's actually like theoretically generalizable and provable. Until they actually make that argument, it's kind of like, it's still a challenge that you have to overcome and you have to demonstrate some sort of advantage eventually, but I don't think it's as threatening as some people make it out to be.
There's also the argument about the storage complexity,
Mm-hmm.
right? That clearly the advantage is much easier to prove.
Mm-hmm.
That the time complexity might be not that dramatically different, but the storage complexity will be.
Yeah, and there's still algorithms that in the quantum computing space that still have yet to be developed and yet to be generated. And so I wouldn't bet against cunning people figuring out better and new quantum algorithms to simulate these materials and actually prove that they're done in better time.
I would like to add with all these points, the paper is not like not being optimistic. It just pointed out that there is not formal exponential scaling yet. And it doesn't mean that one should not pursue the algorithms to really reduce the complexity. Some of the challenges we face for the computational chemistry research. So I would say that like paper has done a good job to bring like theoretical perspective. That's what kind of a scaling one would like to see. And there's like a formal proof or no formal proof, and in practice how things can work. So I would say that overall good paper that we should consider, like how things are being stated. But at the same time, it's not a red flag that one cannot really do quantum computing or like cannot use quantum advantage.
Okay. A lot of people have presented work on variational quantum algorithms today, and so I was wondering, do you think that variational quantum algorithms at scale will be able to achieve chemical accuracy?
No, certainly not. I'm absolutely certain that not. For the biggest obstacle is the number of measurements you have to perform in the operator averaging procedure in VQE. Even if you simulate VQE on a noiseless shot-based emulator, the number of measurements is just intractable as soon as the number of basis functions or qubits is increased. So even if you take the quantum errors out of the equation, so I don't believe so. That said, the variational ansatz concept will still be important in the fault-tolerant era for the preparation of the initial state for QPE or related algorithms.
Any other opinions?
I think at IonQ we're optimistic about variational algorithms for chemistry, right? And I recognize the measurement problem, right? I think there are innovative ways to reduce the number of measurements, and some of these are like exploiting symmetries in the Hamiltonian to measure several terms at once, and then reducing the number of terms you have to measure. And there are also ways that interpolate between variational algorithms as well as exact algorithms like quantum phase estimation. And so, probably I always think from quantum advantage and or reaching some form of success with quantum algorithms, that there's never going to be a step function, right? So often, I think likely scenario would be that you're interpolating between a purely variational approach and a quantum phase estimation based approach. And as your quantum computers get better and better, you can run certain algorithms to the same precision faster, meaning with fewer number of measurements, right? So you're interpolating between a near-term variational approach and a longer-term quantum phase estimation-based approach in kind of a continuous fashion. So I agree that I don't think variational algorithms will lose relevance, but I think it's going to be like a continuous path towards quantum advantage using them.
Anything to add?
Well, I think the measurement problem is is the big Achilles heel in the whole VQE system, right? So unless you have, since quantum computers can't have to sample the Hamiltonian, right? That's always going to be a problem, because as the number of qubits just grows, even if your quantum computer is perfect, you need more and more measurements to make sure your distribution is correct. If you have an emulator that can directly calculate it, then you don't have to sample, but you basically have to eliminate the sampling procedure. I don't know how you do that on a physical quantum computer. So, from VQE on a physical quantum computer, it's an interesting thing. It can give some, interesting insights. But yeah, unless you can get that number down, like the problem is that the sample scale with the size of the system, right? And that's something which is just hard to live with.
I think everyone explained really well, so
Okay.
nothing more to add.
All right. Yeah. So, all right. Well, I guess we should wrap this up. We got 5 minutes left. Just to sum it up, like what would you say are the major challenges facing chemistry applications right now? I guess we'll start with you.
So I would say that still we have really good conventional classical methods that we can apply to. There's no doubt into that. Even CCST parenthesis T can be turned up to for certain organic molecules. So I would say that we do have a strong correlation problem. For example, some of the chemical reaction, if you have some of the species that's really highly correlated. So and that will become one of these limiting, that some of the species are very correlated, and you would like to treat every species at the same level, but same level of matter. But if one of the species is highly correlated, then you have to do this treatment that all the calculations are done at those levels. And then it would mean that whole calculation also becomes expensive. So I would like to see that we reduce, the quantum advantage would be the we can do the whole system at the same level with balance of accuracy and the cost. And this is just for practical reason that we would like to do. I mean, chemistry itself is like not that we need to do only a few calculations. Once you go into research, you have to apply, you do like many calculations, and that would mean that for material discovery or like any reaction mechanism process, you have to spend lots of time, lots of resources. Yep.
Scott, what would you say are the major challenges facing the space?
I think actually one of the major challenges is actually doing the kind of downstream properties that come out of these calculations. It's one thing which has kind of really been missing is, so much focus on just PES curves, PES curves, PES curves. That's great for catalysts. It's great for reaction chemistry. But when we talk about like other chemical properties such as like dielectrics, it's kind of been off the radar, and yet these are properties that are important for various companies and various chemists. Whenever you try to present a simulation package or kind of the results of the simulation to a chemist, they want to see the entire package. They want to see all the properties, as many properties as you possibly can predict it so that they can make the best decision. And I think that's just one thing, it's one thing which has kind of, I think, somehow fallen off the path. It has not been an area of deep focus for a lot of smart researchers, and I think it's one area that we could definitely improve that would have some meaningful impact maybe in the short term.
Sonika?
Yeah, I think we need better algorithms, right? I think we've just started exploring, quantum algorithms for chemistry, and we certainly need better algorithms. And so far, the algorithms we have, we've only been able to demonstrate small molecules running on real quantum computers. So, combination of better algorithms, and then actually running those algorithms on real hardware, and then being able to optimize, maybe incorporate some error sources and improve like the way the ansatz is created, and having co-design between algorithms and hardware. I think if you had a lot more of that, the field would move much more quickly.
Scaling of error correction is the biggest hurdle, I think, but that's kind of obvious for all applications. But I like what Scott said about the methods for determining other properties than just total energies of states. I mean, we can do it with operator averaging on top of VQE, but how do you do it in a fault-tolerant context? I think there is very little research on it, like reduced density matrices or overlap between states or transition dipole moments, this kind of things. But this will come. I think as soon as we start exploring energies on scale, then there will be a strong pull for other applications.